Chapter 6 will really start to get into our applications of derivatives, finding maximum and minimum values, and Chapter 6.1, Section 6.1, is absolute extrema. So I've drawn here a function, y equals f of x. It's increasing from minus infinity until we get to minus 6, the top of this hill, then it decreases a bit, then it starts to increase, then it goes back down. But I'm just going to make a few notes here about the relative extrema. So f of x has, what does it have? It has a relative maximum. It has a relative maximum at, let's say of, we'll give the value first. Relative maximum of, here I have a max, right, at minus 6, so that max value is 7. Has a relative maximum of 7 at x equals minus 6. And another relative maximum of what? Here's a minimum, but I have another top of a hill over here, right? It's got another relative maximum of positive 5 at x equals 3. Of 5 at x equals 3. And the function also has a relative minimum. It has a relative minimum at negative 1 of positive 2. So it has a relative minimum of, what did I say it was, of positive 2 at x equals minus 1. So that's all stuff we've done before. That's relative extrema. This section is absolute extrema. And I won't write down the formal definition of what an absolute max or an absolute minimum is, because it's easy enough to talk about, but if you do want to see it, it's in the textbook. But instead of talking about relative maxes, a relative max would be the peak of, or the top of a hill, right? It's the y values that are bigger than all y values that are nearby it. So this is a relative max, and this is a relative max because they're the tops of these hills. These y values are bigger than anything in a local neighborhood. An absolute maximum is the biggest y value the function ever attains, period. Right? So these are both relative maximums, but this point right here, 7, is in fact the largest value the function ever attains, right? For any x value you plug in, 7 is indeed the maximum. So this is where this comes in this section. It has an absolute maximum. It has an absolute maximum of 7 at x equals minus 6. So what about absolute minimums? Does this function have an absolute minimum? Well, it has a relative minimum right here, right? It's at the bottom of this valley. But an absolute minimum would be the smallest y value this function ever attains. And if you look at this, well, over here, there's a smaller y value than this relative minimum. Here's a smaller y value. Here's a smaller y value. What's the smallest y value this function ever attains? Well, the way the graph is drawn with this arrow, it indicates it just goes off to minus infinity. So it doesn't actually have a smallest value it ever attains. It doesn't have an absolute minimum. So this function has no absolute minimum. And that can happen, right? That can happen if your function goes off to infinity or minus infinity. Then just no absolute minimum ever occurs. So this is the idea of this section. We've already talked about relative extrema. They're fairly easy to understand. Absolute extrema are just as easy. The absolute max of a function is the biggest value it ever attains, and the absolute minimum is the smallest value it ever attains. So this is really what we want to do, right? We've talked about these business applications. We've got profit functions, and of course we want to maximize profit. Well, we're not really always interested in just finding these relative maximums, right? We want the biggest value the function ever attains. We want the most profit possible. So this is really what we want to do. We want to find absolute maxes of functions, which is a slightly different process than just finding these relative maximums. The problem, as we saw in the last example, is sometimes they don't exist. Well, There's one nice case where you're guaranteed they always exist. This is a very famous result known as the extreme value theorem. It tells us when our functions are guaranteed to attain these extreme values, these absolute maxes and mins. So if f is continuous on a closed interval a to b, then f attains both an absolute maximum value and an absolute minimum value on that interval, on the interval a to b. So there's two hypotheses here. Two things must happen. It says if I have this function that's continuous, so one, my function has to be continuous. I can't have any breaks or holes in the graph. And two, this is something we don't talk about very often, but I need it to be continuous and defined on this closed interval from a to b. By closed, I just mean it includes the endpoints, right? I've got square brackets here, so a and b are included. This is important, it's got to be a closed interval. So if I have these two things satisfied, continuous on a closed interval, then I'm guaranteed that my function has an absolute maximum and it has an absolute minimum somewhere on this interval. It's very easy to convince yourself of this. Just take any old closed interval. So let's say this is x equals a. Right, so we're going from a to x equals b. Now my function has to be continuous on this interval, so it's got to be defined everywhere. Just choose a point. Choose a point where choose a value over here at a. So maybe my function value at a will be f of a, right there. And choose a function value for your function over at b. So I'll just choose any little point. Maybe it's way down here. All right. So there's f of b. So my function is going to be defined on this closed interval, including the endpoints a and b, and it's got to be continuous from a to b. So draw something. Draw a continuous function from a to b. Don't care what you draw, just draw something. There's my function. Lots of ups and downs, but I claim this is my function y equals f of x. No matter what you drew, you have to have a highest point, and you have to have a smallest point. In this case, it looks like this is my biggest y value, so there's my absolute max. I also have a relative minimum right here, looks like. I have a relative minimum right here, I have a relative maximum right here, but I have the biggest y value I ever attained, and it looks like the smallest y value I ever attained is over here. There's my absolute minimum. And no matter how you draw this, as long as you go from a point over here on A and a point over here on B, there must, and you're continuous, right? I'm not allowed to lift my pencil from the paper, I'm not allowed to blow up to infinity or anything like that. There must be a biggest y value and there must be a smallest y value. So it's a very intuitive result. It is necessary if you break any of these conditions, if I'm not necessarily a closed interval, then I don't necessarily have to be defined on the boundaries, and weird things can happen. But as long as I have both of these things continuous on a closed interval, there must be an absolute max and a min. So this is really nice. We know we have to attain these things. The only question is, how can I find them? And I want you to note two things that happened over there. The absolute max occurred at a critical number, right? It occurred at this relative maximum. It occurred at this point where my derivative was 0. So the absolute max occurred at this critical number. Meanwhile, the absolute minimum actually isn't at a critical number. It's just at the endpoint. It's at this endpoint b. And it turns out that's the only two things that can happen. These absolute extrema, absolute maxes and mins, they occur either at a relative max or min, in this case the absolute max is at a relative max, or they occur on the endpoints. Depending on how you drew your graph, you might have drawn something that looks different, but they occur either at critical numbers, at relative max and mins, or at the endpoints. So this leads into our algorithm for how to find these things. If these are the only places they can occur, then they're the only places we need to check. So here's our algorithm. Here's finding absolute extrema. Finding absolute extrema. And this will of course be in the case where we're guaranteed they exist, f is continuous on a closed interval. Alright, so f is continuous on a to b. And all the questions will look like this. Find the absolute max or absolute min of some function defined on this closed interval. So here's step one. Step one, find all critical numbers. We've done a lot of this already. Find all critical numbers. For an f in the open interval a to b. So don't worry about the endpoints. By the way, throughout this class I've tried to write f of x all the time because it feels a little more natural, I think, in a business calc class. But when I write just f, I mean the function f of x. Right? So find all critical numbers to evaluate f at all critical numbers. Found in step one. 3. Evaluate f at the endpoints of a to b. Right, what I mean by that is just compute, plug in a and b, find f of a and f of b. And then step 4 is actually kind of obvious at this point. Right, we've made this observation that absolute maxes and mins can only occur in two places, either at a critical number or at the endpoints of the function, at a or b. Right? That's the only places they can occur. So I've found all the critical numbers, and I've evaluated the function at all the critical numbers, and I've also evaluated the function at the endpoints. Well, what's the absolute max going to be? The absolute max would just be the biggest value of all those points, and the absolute minimum would be the smallest value of all those points. So I just take this list of numbers that I have now, I take this list of the function evaluated at the endpoints and all the critical numbers, and I just choose the biggest one. The biggest one is the absolute max, and the smallest one is the absolute minimum. Right, so the largest of the values found in step 2 and 3 is the absolute maximum. And the smallest is the absolute minimum. So that's it. There's not a whole lot different from before, right? We're used to doing this process of finding all the critical numbers. Now I'm saying just plug the critical numbers into your function. We're not going to figure out if they're maxes or mins, right? We're not going to use any first or second derivative test to figure that out. We're just going to plug them into our function. Then we plug the endpoints into the function. Sometimes students forget to do this, by the way. This is very, very important. Very often your absolute max or mins occur in endpoints, so don't forget to do this step. But just plug them all in, and that outputs all the y values. And you just choose the biggest y value as your absolute max. The smallest one you found is your absolute minimum. And that's all the theory in the section. We'll just do a few examples here. So I usually start off with a simple polynomial example. We'll jump straight into a harder one. Here I have a rational function, so not too much harder. But the question is, find all absolute extrema for this function, f of x equals x over x squared plus 4 on the closed interval minus 4 to positive 4. That's an important note, right? This guarantees, because this is a closed interval and this is a continuous function on that closed interval, right? I'm never dividing by 0. X squared plus 4 is always positive. I'm never dividing by 0, so I'm continuous on a closed interval. Extreme value theorem says we must have an absolute max or a min. So how do we find it? Well, we find all the critical numbers. Step 1, we'll find all the critical numbers. I need the derivative. Rational expression, I'll use the quotient rule to find the derivative. It's going to be low d high, the bottom, x squared plus 4, times the derivative of the top, derivative of x is 1, minus the top, x times the derivative of the bottom, 2x, all over the bottom squared, x squared plus 4 squared. And if we clean this up just a little bit, we'll do this all in one go. I've got x squared minus 2x squared. Actually, let's put the constant first. We've got 4 times 1 is 4. So 4 minus x squared minus 2x squared is minus x squared, all over x squared plus 4 squared. Alright, so we want to know, when is this equal to 0? Also, when is it undefined, right? Critical numbers are potentially it's undefined, but the only way we can be undefined is if we divide by 0. X squared plus 4 is never equal to 0. So, let's see. We'll take our derivative and we'll set it equal to 0. Divide both sides by the denominator to just get 4 minus x squared equals 0. What now? A couple of ways you can solve this. How about we do it this way? This means x squared is equal to 4, so x is plus or minus 2. The other way is recognize this is the difference of two squares, factor it to get 2 minus x, 2 plus x. You still get the same thing, x is plus or minus 2. Okay, there's our critical numbers. Step 2, take those critical numbers, plug them into the function. So f of positive 2 is 2 over 2 squared plus 4 is 2 over 8, or 1/4. Plug in the other critical number, f of minus 2, that's minus 2 over minus 2 squared plus 4, that's minus 2 over 8 is minus 1/4. So step 2 is evaluate the function at the critical numbers. Step 3, don't forget about the endpoints. Right? These are, if these critical numbers correspond to relative extrema, these are the values of those relative extrema. But the absolute max or min might not occur to relative extreme. It might occur at the endpoints. So we'll plug in the endpoints and check those quickly as well. F of minus 4 is minus 4 over minus squared plus 4. That's minus 4 over what? 16 plus 4 is 20, is minus 1/5. And last but not least, f of positive 4 is positive 4 over 4 squared plus 4. That's 4 over 20 is positive 1/5. So the only places maxes and mins could occur is at critical numbers or at the endpoints. Well, here's the value of the function at all these points. The biggest one must be the absolute maximum. What's the biggest value we have here? 1/4, I believe. 1/4 is bigger than 1/5. So there is my absolute max. Absolute minimum, minus 1/4 is smaller than minus 1/5, so right here, there is my absolute minimum. And the question did not ask where did they occur. If I want to know where they occurred, it would be the x values right here. But when it says find the absolute extrema, it wants the y values. It wants the actual values of the function. Alright, we'll do another one. I won't write the words, so I'll just put up the function. It's ln of x over x on 1 to 3. Closed interval 1 to 3. Find all the absolute extrema. Good example to try and do it on your own. Pause the video here if you want. Try and do this. It'll be the exact same process as last time. Find the critical numbers, evaluate the function of the critical numbers and the endpoints, and choose the biggest and smallest values. So pause it if you want, but I'm going to keep going now. So step 1, we'll find the critical numbers. We need the derivative. Once again, this is written as a quotient, so we'll use the quotient rule. Low d high, bottom times the derivative of the top. Derivative of ln of x is 1 over x. Minus the top, ln of x, times the derivative of the bottom, derivative of x is 1. All over x squared, the bottom squared. So actually a really nice derivative. X times 1 over x is just 1. 1 minus ln of x over x squared. Okay, so we're looking for critical numbers. Where is this undefined? Well, it's undefined for x equals 0 or any negative value for x, right? Because natural log is undefined. But that's not in the interval 1 to 3, so I don't have to worry about it, right? I'm only looking for critical numbers in 1 to 3. It's also undefined when x is 0 because that causes division by 0. But once again, x equals 0 is not in 1 to 3, so I don't care about it. So I don't have any undefined critical numbers. What about when this derivative equals 0? 1 minus ln of x over x squared, when do equal 0? Well, that's when the numerator is 0, so that means 1 minus ln of x is 0. That means ln of x must equal 1. So what does that mean? That means, just converting this to an exponential expression, that means my base, e to the 1, must equal x. So that means x is e. And that's it. That's our only critical number. So we're already on step 2. Hopefully you appreciate that these problems, if you're good at them and you know the algorithm and whatnot, they actually don't take that long. So step 2, plug in our critical number. F of e is ln of e. By the way, I should have checked. I should have asked, that critical number we got, e, is it in this interval? If it isn't, I throw it away. But e is 2.7 to 2.71, something like that. So that's definitely in this interval from 1 to 3. So f of e is ln of e over e, which is just 1 over e. ln of e is equal to 1. Step 3 is we plug in the endpoints as well. So we're going to plug in 1 to get ln of 1 over 1. But ln of 1 is 0, so that's 0. And we'll plug in the other endpoint, 3, to get ln of 3 over 3. Now I'm pretty good with numbers. I can usually look at things and figure out which one's bigger. 1 over e, 1 over 2.7 or so, ln of 3 over 3. It's actually very hard to decide which one of these is bigger than the other because they're very, very, very close. So I plug them into a calculator. This is approximately, I have it written over here. 1 over e is approximately 0.368, and ln of 3 over 3, that's approximately 0.366. So what's my absolute minimum? Well, the smallest value I have is 0, occurring at the left endpoint 1. There's my absolute min. And what's the biggest value I attain? It's 0.368 is just a little bit bigger than 0.366, so 1 over e. 1 over e would be the value I enter into my math lab if it wants an exact answer. If it wants it rounded to 3 decimal places, 0.368 is fine. But this is the biggest value it ever attains. There's the absolute max. So one of these is occurring at the endpoint, right here at 1, and the other, the absolute max, is occurring at our critical number, just ever so slightly bigger than the value of the function at 3. So we'll just do one more. It's sort of the same process every time. And surprisingly to me, students tend to struggle with this. And I think it's knowledge of the algorithm, right? It's knowledge of, it's knowing what to do. But the steps are the same every single time. Find the critical numbers, plug them in, plug in the endpoints, and choose the biggest and smallest. That's all there is to it. So last one, here's my function. F of x is e to the x cubed plus 3x squared minus 9x on the closed interval 0 to 3. So first step, critical numbers, take the derivative. What do we have? We've got e to a function of x, so we're looking at our special case of the chain rule number 2. The derivative is e to that same function times the derivative of the exponent. 3x squared plus 6x minus 9. And I'm going to go a little bit further with that. I'm going to factor out a 3. So I'll write that as 3 times x squared plus 2x minus 3 times e to the x cubed plus 3x squared minus 9x. So I want the critical numbers. Is this ever undefined? Well, polynomials are defined everywhere, exponential functions defined everywhere. So this is defined for all values of x. The only question is, can it equal 0? I shouldn't say implies. Can this equal 0? So I take I'm just going to set equal to 0 right now. It's not completely correct to string these equalities together because I'm technically saying my derivative is equal to 0. It's not. But I'm solving this equation. Right? I'm solving this equation. When is this equal to 0? Well, remember, I've got a product here. So the only way this can be 0 is if this expression is 0 or this is 0. Exponentials are never equal to 0. So the only way this can be 0 is if this is x squared plus 2x minus 3 is equal to 0. Hopefully it factors. Two numbers that multiply together to give minus 3, add together to give plus 2. I'm probably looking for plus 3 and minus 1. That sounds right to me. And that means that our critical numbers are either x is positive 1 or x is minus 3. Well, hold on. Our closed interval is only from 0 to 3. Minus 3 is not in that interval, so I'm going to get rid of it. Right? I might have a relative max or min there, but I don't care because it's not in the interval that I'm looking at. And that's all the work. It really is all the work, right? Finding the critical numbers. Hopefully you don't find it too bad because we've done this for the last several sections, finding critical numbers of functions. It's a process of finding the derivative and then doing the algebra. So we have one critical number in our interval, x, I've half erased it here, x is positive 1. So now we plug them in. Find the value of the function at 1. That's going to be e to the 1 plus 3 minus 9. That's e to the minus 5, or 1 over e to the 5th if you want. And we'll plug in the endpoints. F of 0 is e to the, that's an easy one, e to the 0, which is 1. And f of 3 is what? F of 3 is e to a pretty big number. e to the 3 cubed is 27, plus 3 times 9 is 27, minus 3 times 9 is minus 27. That's e to the 27. So what do I do now? I just choose the biggest and smallest values. What's the biggest one? E to the 27 is gargantuan. That's a huge, huge, huge number. Well over several million. So there's the absolute maximum. And what's smaller, 1 or 1 over e to the 5th? Well, 1 over e to the 5th is like 1 over 100, more or less. So clearly, e to the minus 5 is the smallest value. There's the absolute minimum. And once again, I haven't really sort of phrased any of these problems we've done. In the interest of time, I haven't phrased them with all the business words around it, right? I haven't posed these functions as being cost functions or anything. But you'll see some for homework that will be like that, and the process is exactly the same, right? Your cost function is still just a function, and if you want to find the absolute minimum value of a cost function on some interval, you differentiate it to find the critical numbers, plug in the critical numbers, plug in the endpoints, and choose the smallest value would be your absolute minimum. Thanks.